volts, W over L is 10, and lambda is 0. So this question here says to we'll go to the actual what it says to calculate the GM of the transistor and draw the small signal diagram of the amplifier. It turns out that this particular problem the author did not draw the small signal. However, it did calculate the gain of the amplifier compared to a BJT. So GM, this term G sub M here, basically is actually being extracted from the gain equation. So there's no real equation given for G sub M. So we'll review this small signal part that we started earlier. So we've got a Mosfet transistor, and it basically on its gate has a DC battery, and then it has a small signal waveform. You understand the Mosfet, in order to amplify the DC, the larger output, the Mosfet must operate in the saturation mode. So just a reminder to have our table for these different modes of the MOSFET. So this is our equation for the saturation mode of the N-channel MOSFET. And the drain current now has the DC drain current plus it has an AC current in there. And without actually solving any particular problem, we can take this G sub S and then separate it out into a DC plus an AC component. And then we'll square this term, and we get three terms at the lower part here. It's our first term, our second term, and then this is our third term we get from that. So if we try to get everything in terms of I sub D, basically we have I sub D over here. The parameters begin to have a similarity. This Kn prime W over L appears in each one of these. So we can divide that term, we can cancel that term out because it's a common term. So this first term, this is the DC term. This is what we use to solve for DC current in the amplifier. And it's a linear term, even though it has the square on it. The second term also is a linear. This is definitely a linear term. It doesn't have any square component. The third term, though, has a square on the small signal AC input. And this is a kind of a troublemaker term here because this is actually distortion. This is what we call clipping on the output of the drain of the MOSFET. So we'll call this one the undesired term. And if we want to, when we design a MOSFET, we want to minimize this term that has this square on it. So we take the desired term Kn prime W over L times VGS minus V threshold times VGF, and we make it much greater than this undesired term. And again, these Kn prime W over L, they cancel. So the formula that we get as a result is the small signal AC input, VGS of T, is much less than 2 times the DC gate to source minus the threshold voltage. And this is similar to the small signal BJT, however, we'll find that there's a significant difference in it. So if we take this equation, and we'll take this part of it, we'll let V sub gate to source minus the threshold equal 1 volt, and then we'll calculate how small should the V sub GS signal be. So here, we're going to say this is equal to 1 volt, and then we want to get a kind of a rule of thumb of how small V sub gate to source AC should be. And a rule of thumb is to put a 1 to 10 ratio between the two. So we can have this gate to source AC is less than 0.1 times 2 times this term here, which is 1 volt, so that's equal to 0.2 volts. And if we recall in BJT amplifiers, this was 10 millivolts. So MOSFETs are capable of handling a much larger AC input before they begin to create distortion. And then that note at the bottom is just a reminder about the 10 millivolts on a MOSFET. So to calculate small signal gain for the MOSFET, we have G sub M. And what is G sub M for a BJT? What is G sub M for a bipolar junction transition?
The formula, or what is it? What is it exactly?
These are G sub M for a MOSFET. You're asking, what is G sub M for a BJT transition? What's the equation for that? And you want to make sure these are on your formula sheets.
Like the 2 is divided by beta over beta plus 1.
Like beta or beta plus 1, is that alpha?
Yep.
It's alpha. So G sub M is 1 over small RE. That's what BJT transition. So you notice the small RE is the AC resistance and the emitter of the BJT. So you notice the difference in the formula. Quite a bit of difference between them. The MOSFET depends on its gain, depends on the voltage difference between the gate to source and the threshold. Whereas in BJT, the gain only depends on the small signal AC resistance. So if you want more gain in BJT, you want to increase G sub M, so you decrease small R sub E. So BJT is fairly straightforward to increase the gain. Your MOSFET, though, in order to increase the gain G sub M, the difference between VGS and the threshold has to get larger, and then there's a second equation for G sub M MOSFET, which is Q times the drain current of the gate to source minus the threshold voltage. So if we keep the drain current constant, we can still change this variable V sub gate to source minus the threshold. And then the third formula for G sub M and MOSFET is square root of 2 Kn prime W over L times the drain current. So this formula here, we can design a MOSFET ourselves by changing the width over the length of the gate terminal on the MOSFET. So if you're designing you find yourself designing MOSFET, this is probably the equation that you'll be using, because MOSFETs can use or require the engineer actually designed to the transistor, whereas in BJTs are pre-designed, and now you just basically decide how much gain you want the transistor to have. So which one is the G sub M that we should use in a problem? It's related to what information is given when you're solving for small signal gain. Km prime WL is probably given, and if not, basically you're probably going to have to use this middle formula to solve it, which means you need to know the drain current, the gate to source voltage, and the threshold here. Now, drawing a small signal MOSFET model, recall that for the final exam, you want to, from memory, draw a small signal BJT model. So this is a simplified MOSFET have different levels of models. This is probably a level 1 model. It's a pretty simple model here. You notice the gate, and when you're kind of remembering this, why is the gate floating here? There's nothing attached to it. The gate terminals, there's no wires on it.
Is it like the like our regular DC MOSFET where it doesn't connect?
Well, what's the current in the gate of a MOSFET? I sub G, what is the gate current?
I sub G?
Zero.
Is 0. So if there's no gate current, that means the gate is not connected to any part of the MOSFET. And that's why in the model we just draw a small line here, which shows completely isolated from the rest of the MOSFET transistor. On the source here, the GM gate to source terminal voltage supply, and then on the drain here we have RO. That's similar to a BJT. And then over here on this side, you notice the drain shows two terminals here on the drain. So when you're practicing kind of drawing this, you probably want to draw it several times. It shows two gate terminals, two gates on here, and it shows two connections for the MOSFET. So it's really different from a BJT small signal model. So you want to practice on paper drawing this circuit, just in case this question actually comes up, to draw the small signal model of the MOSFET. MOSFETs have an early voltage, D sub A, and if we get the gate to source voltage versus the drain current, we can draw these different MOSFET curves based on the gate to source minus the threshold, and then we project a line from them, we intercept this axis at a negative voltage, and that's pretty much the same as a BJT. So we'll just call that number early voltage, just like we do with a BJT. So we mentioned this lambda function before, and normally we would use lambda equal to 0. Whenever you have a MOSFET problem, if lambda is not given, then you do not want to put this in your equation. So there's no question what is lambda. If a problem does give a lambda value, these are some typical numbers, 0.005 less than equal to 0.03. And PSpice uses lambda. So your core 2 problem with the MOSFETs may have some difference, I'll say minor difference from PSpice. And the reason is PSpice actually interprets a lambda. But you notice how small lambda is, so this drain current calculation, if you disregard lambda, it's not really going to change your current very much. So this is called a spice level 1 model. And then there's a note here when if you are manufacturing or making your own MOSFET, whenever the gate length falls below 2 to 4 micrometers, then you generate large errors in this model. And that's one of the issues that over time, because these transistors were made smaller and smaller, they begin to produce lots of errors in the model split. So the warning is here. Uses only a level 1, and if your gate length goes below 2 to 4 micrometers, you can generate large errors. So on your homework 2, note the length of the gate on the NMOS and the PMOS, and you want to examine this number. As long as the number for your gate length is above this, then your P-SPICE simulation should agree somewhat with your paper design. So RO, the collector, the drain output resistance, is this the same equation for BJT? Is that the same equation for microwave junction transistor? Collector current and the BJT, here is the drain current. It's basically the same equation for a BJT, where the drain becomes the collector current. So RO is the small signal resistance of the collector, the BJT. So now we find the similarity between BJT analysis and MOSFET analysis. If lambda is not equal to 0, basically your 3 formulas here, these are the 3 formulas that we had for the device. 2 of the GM formulas must be adjusted to include lambda, and 1 is invariant to lambda. So we take these 3 GM formulas. This formula here, we can add lambda here, and in the 3rd formula, we can add lambda at this point. And again, if a problem does not state a lambda, actually give a lambda, then there's no need to include it in your G sub M calculation. This is an advanced topic. This is a high frequency MOSFET. This is not a device that we're actually studying. When you draw its small signal model, instead of the gate floating, a capacitance is put between the gate and the drain. So we have a capacitance here, and then there's capacitor between the gate and the source. So this model is different from the low frequency model. So we're not really using this model here. Notice this gives G sub drain, so that's the admittance. That's 1 over R sub O. So if you're asked to draw this MOSFET model, you can draw this model, or we can draw the earlier small signal model. But we're not actually using a MOSFET with capacitor in the model for it. So this is actually the problem from an earlier final exam. we can go back to the, I guess we can go back to the earlier. Where it appeared in this, it's the same problem. And the case of N, it was 0.1 milliamps for vote squared. The threshold vote is 1 vote, and WL is 10. So this problem is saying lambda is equal to 0, so there's no need to include lambda. Now what this problem is asking is, it's asking, we'll go to this one. This is probably more likely to be something we would be concerned about. It says find a small signal transconductance gain GM of the transistor and draw the small signal diagram. So this equation H of D is minus RG over RG plus R signal times G sub M times RD in parallel with RL. That's the same equation used for a BJT amplifier, because G sub M is 1 over RE for a BJT. So part of the reason we do BJTs first is because when we get the small signal, we start using pretty much very similar formulas. So this question was asking, what is G sub M? Now to solve that, we had to, a couple of diagrams were given for the circuit. So this diagram here, this is the input to the MOSFET. And then the diagram over here, this is the output from the MOSFET. So the question is asking, what is the small signal voltage gain of the MOSFET? So on the input signal goes from 10 millivolts on peak to minus 10 millivolts minimum. And then on the drain, the peak is now 2.6 volts, and the minimum is 2.4 volts. So this is the same as an oscilloscope. This is channel 2, and this is channel 1 on the oscilloscope. So the gain of this circuit then is the same as we're using an oscilloscope in channel 2. And the MOSFET, you notice the peak here is the minimum here. So MOSFET flips the input 180 degrees. So when we calculate the gain of a MOSFET, we subtract the minimum from the max, and that's we don't really do that for a BJT. We want to make sure we get the minus 10. Now, we could have just said 2.6 max minus 2.4 minimum divided by the input is 10 millivolts peak minus 10 millivolts minimum, so the gain is minus 10. So if this appeared on the exam, we really couldn't solve the next problem unless we had understood what this was. Now this also, in order to solve this problem, we needed to find the total drain voltage here. So on the oscilloscope, and oscilloscopes have a DC offset. So the DC offset here was 2.5 volts, and that's the drain DC voltage. So the voltage on the drain end is the battery, 5 volts minus ID R sub D. The only unknown is I sub D, which is 0.5 milliampere. A problem like this is here is very involved, but it's actually really straightforward because it gives the information, and it just relies upon your understanding how do you interpret these spots. So this is something you want to basically study for the final exam. How do we actually get the gain of minus 10 here? And then how do we get the voltage, the DC voltage? It's actually given that it's 2.5 volts on the drain, and now we use this equation to calculate the I sub D, which is half a million. So with that, the next question can be responded to. The gain is minus the gate resistance. The gate resistance is just this large resistor here. And the gate resistance is 10 megohm, 1 megohm. And then that's times the drain resistance parallel to the load resistance. So, and then it actually to extract G sub M. So this is G sub M calculation for that. And just note any questions that I am not really going over. You won't expect questions like that on the final exam. So this question here is saying determine the width over length and the gate voltage to ensure the transistor is in saturation mode and has the required DC current. So this is kind of a reverse engineering part of this exam. It's asking to extract the width over length for this circuit. And this is, when completing this exam, and the width over length is 3.154 milliamp per volt. When the exam was started, the width over length for all of the problems was 10. So some became confused by the two different, and I don't know whether they were actually able to complete this part of the problem. So we won't have a problem such as this, where you have to extract the width over length. Width over length will usually be given